In 9.4, we looked at tangent ratios. Now we're going to add on sine and cosine ratios. Okay, so thing about tangent, when we used it, we only did opposite leg over adjacent leg. Okay, but sine and cosine bring in our hypotenuse. Both of them, the hypotenuse is always going to be in the denominator. Okay, but sine is going to use the opposite leg, and cosine is going to use the adjacent leg. And so as we start to think about all these, sine, okay, of an angle is equal to your opposite over hypotenuse. Cosine of an angle is equal to your adjacent over hypotenuse. And then tangent of an angle is equal to your opposite over adjacent. Okay, so there's some different ways that you can remember these. Some people remember SOHCAHTOA, and so if you look at all of these, just the first initial, you have sine, opposite over hypotenuse, so that does the S-O-H. You have C-A-H, SOHCA, and then T-O-A, TOA. Okay, SOHCAHTOA. If you were to look up some other different ways, there's several different ways to remember it. I know one of my teachers always did some old hippie caught another hippie tripping over algebra. Okay, again, it's just using all those letters. But whatever way helps you remember is fine. So that way you can remember, you can distinguish the difference. So you can think about sine, you can remember it's opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. But also know that if you have your notes with you, you'll be able to just refer to them very quickly and just be able to have them written down and be able to know, okay, well, I need to do the sine because it uses opposite over hypotenuse or whatever you're looking at. So we look at this next problem. We're going to go and jump in because we already kind of know how these work. They work the same way, just like tangent. And so when we look at sine of S, okay, that's the first one it asks us to find, sine of S. Okay, this isn't sin of S, it's sine of S. That's just the abbreviation is S-I-N, sine of S. And so, if this is my reference angle, opposite across from it, we have our 63 here. We have adjacent side is 16. And we have our hypotenuse. Obviously, it's always across from our right angle. So when I'm doing sine, sine is equal to my opposite over my hypotenuse. Okay? So, the so part of SOHCAHTOA. And so my opposite of this is my RT. My hypotenuse is my RS. And so if I plug those in, my values are 63 over 65 would be my fraction. And then it says to do the decimal, round it to 4 decimal places. So when you type this in, then you're going to get 0.9692. Would be 4 decimals, okay? And that would be approximate because we rounded it. So I'm just going to change the symbol here instead of equals. It's the approximate. So the sine of S would be approximately 0.962. Okay, so then we also need the sine of R. Okay, but before we go to that, I'm going to go ahead and do cosine. I'm going to leave my reference angle the same for now. So let's do the cosine of S. Okay, so cosine is our adjacent over hypotenuse. So instead of doing RT, now we're going to do the side closest to it that's not our hypotenuse yet. So the adjacent side is ST over our hypotenuse of RS. So now we have 16 divided by 65. And so then we're going to plug it in to get a decimal into our calculator. And so we get 0.24615, but 4 decimal places, so I need to round it. So it's going to be 0.2462. Okay, and again, this is approximated, so we're just going to change that right there. It's the approximate number of 0.2462. Okay, so those were our 2 answers for those. Now let's go ahead and go to R. So now we're changing our reference angle. Okay, so I'm just going to do it in a different color. So if I'm doing R here, now my opposite is going to be over here. Okay, it's going to be the ST. My adjacent is going to be right next to it. My hypotenuse doesn't change, right? Hypotenuse is still the hypotenuse on a right triangle regardless. but my opposite is different whenever I'm doing a different angle. Okay, so now if we do sine of r, okay, and we already said sine is opposite over hypotenuse. And so if I do opposite of r, now is my st over my hypotenuse of rs. If you notice here, this is the same as the cosine of s was. So that means we're going to have the same values to plug in. So I have 16 over 65, and it's going to give me the same decimal. It's going to give me approximately 0.2462. Now if we do cosine of r, okay, cosine of r gives us our adjacent over hypotenuse. So our adjacent to r is rt over hypotenuse of rs. Again, notice these are the same. Okay, between sine of s and cosine of r, they're the same. And so when we keep going along on that, it's going to be 63 over 65, and it's going to give us the same decimal as we did the first time of 0.9692. Okay, and so as like I was saying, if we notice sine of s and cosine of r, okay, the different sine of s and cosine of r are the same. Sine of r and cosine of s are the same. Okay, so if we look at this next concept that we have here, it tells us the sine and cosine of complementary angles, right? When we look back at the problem that we just did, I'm going to flash back real fast, s and r are complementary, right? Because they're in a right triangle. So if s was, say, 40 degrees, that would mean that r would have to be 50 degrees, okay? In order to make the 180 in the whole triangle, s and r add up to be 90, so that makes them complementary. So this concept tells us that when we have our complementary angles, the sine and the cosine of its complement are going to be equal to each other. Okay, and that's just what we just saw in that problem. So the sine of A is equal to the cosine of the complement. So complement, remember, is our 90 minus our angle. The complement of A is subtracting A from 90 to get what's left over. And so it's equal to the cosine of B. The cosine of A would equal sine of B. Sine of B is equal to cosine A. Cosine B is equal to sine of A. This is what we just saw in the problem before. Okay. Now, do you have to know this? No, not necessarily. You can usually just figure it out. But if you do, then it just kind of helps you be able to have some shortcuts in working your problems. So in example 2, we want to write the sine of 56 in terms of cosine. Okay, this is just trying to get you familiar with the one that we just looked at, being able to do that concept. So if I did sine of 56, we want to write it in terms of cosine. So we know it would be cosine of the angle that was opposite of it, right? Okay, so the cosine, it would be cosine of its complement. So its complement, in order to find it, we would do 90 minus our 56. And so if we just solve that out, we would get cosine of 34. Okay, so writing sine in terms of cosine would just be cosine of 34. Okay, all you do with that is just, if it gives you sine and you want to write it in the opposite, then you just have to subtract it from its 90-degree angle to get what the actual other angle would be in that triangle. So now to example 3, this is kind of like what we looked at in 9.4, when we're kind of like, what's the point of these? What helps us to be able to find angles, and it helps us to be able to find side lengths. And so in this case, we want to find the values of x and y. And so we have only one reference angle here. We have this 26. And so that means we know our hypotenuse is always across from our right angle. Okay, and now our opposite would be over here with the x, and the adjacent would be here with the y. Okay, because 26 is our angle, adjacent's right next to it, opposite's across. So when we're solving for side lengths, okay, one of the keys to think about is I'm going to use, first of all, whatever side length I'm looking for. Okay, so if you notice here, if I want to solve for x first, well then I would need to use the opposite, a function that has opposite in it. Then you also need to use whatever side length you know. Okay, so if I were to use the opposite and the adjacent, it wouldn't help me because they're both variables. I have no way to solve that if I have two variables. Okay, but my hypotenuse, I do know at 14. So if I'm looking for a function that has opposite and hypotenuse, that's going to be my sine function. Okay, and in step 1, I already showed that to you. So I would end up doing the sine of my 26 because that equals opposite over hypotenuse. That's my SOHCAHTOA. S-O-H. Opposite over hypotenuse. So x over 14. To solve this, right now x is being divided by 14, so I need to get rid of that division. So I'm going to multiply by 14. And so I get that x is equal to this 14 sine of 26 would equal my x. So all I have to do is just type that in. Again, this is just a function. When you type it into your calculator, you'll find the button that says SIN for sine. And so you do 14 sine of 26. Like I said before, the sine part, it'll give you parentheses to put that 26 inside of it. And then the 14 is just being multiplied with it. So when I do this, I get approximately for x. And it said nearest tenth up here. Always make sure you read. Go back and make sure you read what you're rounding to. So nearest tenths is 1 decimal. So I'm going to do 6.1 would be approximately my length of x. Okay, then I also need to find y. So if I go back to my problem here, okay, y is my adjacent. And then again, I'm going to use whatever side I have, which is my 14, which is my hypotenuse. So now adjacent hypotenuse is my cosine function. So cosine of 26 would equal my adjacent over hypotenuse, so that gives me y over 14. Again, y is being divided by 14, so I'm going to multiply by 14. And so that cancels, and so I get 14 cosine of 26 is equal to y. And so when I multiply that out in my calculator, I'm going to get 12 point, and it's 5/8, but nearest tenths place is 1 decimal, so I'm going to have to round it. So 12.6 is approximately the length of y. In example 4, it tells us to find the sine and cosine of a 45-degree angle. Okay, remember a 45-degree angle would tell us that it's a special right triangle again. So when I have a special right triangle, I have this 45, 45, 90, right? Okay, and my side lengths are x, x, x square root of 2, but if I plug in a 1 for x, I'm just going to do 1, 1, and then the square root of 2. Okay, so if I use this one as my reference angle, it doesn't really matter. Okay, that would make this my opposite, this my adjacent, and then my hypotenuse. Okay, so if I want to find the sine of that 45-degree angle, then I would do my opposite over hypotenuse, so I would do 1 over the square root of 2. I need to rationalize that, remember we don't like radicals in the denominator, so I would multiply both the top and the bottom by my radical. So on the top I get the square root of 2. The bottom I multiply what's under the radicals, so I get square root of 4. And then the square root of 4 reduces down to be 2. So sine of 45, I get square root of 2 over 2. Cosine of 45, we do adjacent over hypotenuse, so that's 1 over the square root of 2. If you notice, these are the same. So when I rationalize them, they're going to be exactly the same. So this one will also equal the square root of 2 over 2. And this would make sense, right? Because sine of an angle is equal to cosine of its complement. Well, cosine of its complement is going to be cosine 45. Okay, so they are actually equal to each other. So you get the same thing either way. Let's go ahead and add on one more thing too. If I wanted to find the tangent of 45, okay, tan is my opposite over adjacent, so I end up getting 1 over 1. So it just reduced down to 1. So tangent of my 45-degree angle is just 1. Example 5, for the sake of time, I'm going to go ahead and skip it. It works just like the problem before and just like the problem we did in 9.4. So you're just using your special right triangle again. This would be a 30, 60, 90 triangle. If you have trouble trying to work it out, then just please be sure to ask questions. And then as we look at this last problem, right before we learned last lesson that we have angle of elevation. We said elevation is when we are at horizontal and we look up. It's the angle that's going up above horizontal. Now we have angle of depression. So angle of depression is going where we look down. Okay, when you're at line of sight, you're at horizontal and then you drop down. So a lot of times this is when you're up higher. So like in this example 6, she's on a mountain and so she's looking down a hill. There will be times where you're saying like the angle of depression from looking out a helicopter is. And so angle of depression, think about depressions like when somebody's very sad, they're very down, or if you depress something, it's pushing down on something. And so when we look down from that line of sight is our angle of depression. And so in this example, it says you're skiing on a mountain with an altitude of 1,200 feet. So altitude means obviously basically from the ground level up, okay, that's that height of 1,200 feet. And it says the angle of depression is 21 degrees. And it says find the distance x that you would ski down the mountain to the nearest foot. Okay, so in height-wise, she's going from 1,200 feet down to 0. Okay, but they want to know that what's the actual distance that she physically skied down. So in this case, we have this right triangle. And so we have this angle, 21 degrees here, that angle of depression. And so if we look at it, we have our hypotenuse here would be our x, okay, because our right angle over here. And it doesn't really matter which triangle you look at. I'm going to ignore this half of the triangle, and I'm just going to look at this part up here. I'm just going to look at this top part of my triangle. Okay, so we have our hypotenuse there, and then we have this 1,200 would be opposite of 21, right? It's not the adjacent because it's not touching it. It's across from it, so it's opposite. And so we have right now, like I said before, you're going to use whatever one you're trying to find. So I'm going to use my x, so I'm going to use hypotenuse, and then I'm going to use the value I know of 1,200. So if I look at this, this is opposite and hypotenuse. The function that uses opposite and hypotenuse, if you think about SOHCAHTOA, okay, SOHCAHTOA, SOH, this OH here is opposite and hypotenuse, so that leaves me with my sine function. Okay, so we're going to take the sine of 21 would equal our opposite over hypotenuse, so 1,200 over x. And so one way we can do this is we can multiply by x because we want to get that x out of the denominator. Or another way that you can do this is when I have one thing in the top and one thing in the bottom. I can also cross multiply this, or I can actually switch places of two items. And so this is something I can show you. To show you both methods right now would be a little bit confusing, but I am going to show you, we're just going to cross multiply these. Okay, when I have that equal sign in the middle and I have a fraction, technically this sign over 21, it can be over 1. I can always add that 1. And so I'm going to cross multiply. So I'm going to get, and if I move this kind of down here so I can see it, I would get x times sine of 21 would equal 1,200. I need to get x by itself, so I'm going to divide by sine of 21 to both sides. So that cancels that part out. And so I'm just left with x is equal to 1,200 over the sine of 21. So that's just plugging it into your calculator again. And so when you plug this in, you should get a decimal. It tells you to round to the nearest whole foot, the nearest foot. So I would get that x is equal to 3,349 feet would be my answer. And it's approximately 3,349 feet.